Assalamu alaikum. Today we will start a new topic, that is the effect of corona and the corona loss, that is the loss that takes place because of the corona. What is this corona effect? Actually, it results in the ionization of the air surrounding the power conductor. There are lots of free electrons present in the free space because of the cosmic rays and radioactivity. Since conductor is at higher potential, it has some electric field, and in the presence of that electric field these electrons will be accelerated, and if the speed of these electrons is high enough they may dislodge the electrons of the other air molecule electrons, and with this the number of electrons will increase. Now these electrons will again be in the same electric field and they will be again accelerated and they will again dislodge the other normal electrons which are bound in the air molecules. This is actually a cumulative process, and when an avalanche of electrons takes place, such type of effect is known as corona effect, and it is accompanied with the energy loss because dislodging of electrons or making electron to move, it requires some energy. That energy is taken from the power conductor, or we can say power system. So in this case we see that this corona effect results in power loss, and also it has one more disadvantage, since it results in the inclusion of the third harmonic component in the current. So when the current, apart from the fundamental component, it results in introduction of the third harmonic, it becomes non-sinusoidal. These are the two main drawbacks. That is, one is the non-sinusoidal current. The second one is the power loss. Due to non-sinusoidal, it results in the communication interference. We can say there are three disadvantages, but it has some advantage as we will see it later. Let us start with the definition of this corona phenomena. It is defined as self-sustained electrical discharge in which the field intensified ionization is localized over a portion of the distance between the electrode. It means the same which we have just described or explained. That means electrons get accelerated and they destroy the electrons, and such type of avalanche of electrons are very close to the conductor. It results in the discharge of this type of electrons, and which are because of the electric field. We can also say that corona is a potential discharge and takes place at the surface of the transmission line conductor when the electrical stress, that is electric field intensity or surface potential gradient, that's one of the same thing, of the conductor exceeds the breakdown strength of the surrounding air. Since we know that, I don't know whether I have told you or not, there is a particular breakdown strength of every material. Beyond that it becomes conducting. So we can say it is a potential discharge, uh, and it takes place, as we know, that at the surface of the conductor or around the surface of the conductor. So when the voltage of the conductor goes beyond the breakdown strength of the air, it results in the breakdown of the air, and that part of air becomes conducting, or we can say there is a lot of electrons which are available. So the voltage at which at which the breakdown of the air occurs with respect to this conductor is known as critical disruptive voltage, that actually break down the air, and this corona takes place. We'll first calculate that breakdown, this critical disruptive voltage. Let us take a simple example of having two conductors having A and B, where A has a charge of Q, similarly B has a charge of minus Q, is a return conductor. You'll see that this N is at the middle of the two conductors. Let P be a point which is at a distance x from the center of the conductor A, and D is the center to center distance between A and B. N is neutral point because in this case you will see that it is equidistant from charge Q and minus Q, and potential at N will be equal to 0 because that potential will be equal to V. I will write it Vn will be equal to Q divided by 4 pi epsilon 0 into D by 2. That is the potential with because of this charge, and because of this charge will be equal to minus Q divided by 4 pi epsilon 0 d by 2, which is equal to 0. This is a neutral point. That's why it is a neutral point. Again, we assume charge to be charge per unit length. Now we will calculate electric field at point P, which is at distance x, because of charge q and charge minus q. That will be equal to q divided by 2 pi epsilon 0 x, because we are calculating the electric field at a point x from an infinitely long conductor. Last time we have calculated this will be equal to this expression. It is not inversely proportional to distance square. It is inversely proportional to distance only, because it is a cylinder, and we have assumed q to be charge per unit length. So this will be equal to q divided by 2 pi epsilon 0 x plus q divided by 2 pi epsilon 0 d minus x, because this point is d minus x from the center of the conductor B. Now both of them will be plus, because the electric field at point P, due to this, I can write it as like this. This is EA, and EB will also be in the same direction. Definitely EA will be greater than EB in this case, but they will be added. That's why I have written it here plus. So by simplifying it will be q by 2 pi epsilon 0 x 1 by x plus 1 by d minus x. Potential difference between the conductors that can be taken from using this equation. This electric field will integrate the electric field line integral of the electric field from the surface of this conductor to the surface of this conductor will give us potential difference between A and B, or the electric field integral from the surface of this conductor to the surface of this conductor. That we have written over here. From the surface of this conductor, that is d minus r, we have taken this to be origin, and this point, the surface of this conductor will be here. It will be, because from here to here it is r, we are considering both of them to be of same radius, and it will be from d minus r to r. So by employing this equation, we'll get q by this and this, and finally the final expression will be equal to this one. You just have to calculate it. It's very simple. Final expression is v is equal to q by pi epsilon naught ln of r by d. This is the derivation for the voltage between these two conductors. So from this equation, q can be calculated as q is equal to v into pi epsilon naught divided by ln of d by r, because we have calculated v is equal to q divided by pi epsilon naught ln of d by r. So we take here q to one side and other parameters to other side, because we want to actually calculate this electric field. We again go back to the electric field equation. It is equal to q by 2 pi epsilon 0 1 by x minus 1 divided by d1 x. So in place of q, we will write this v pi epsilon naught ln of d by r. So here pi epsilon naught will be cancel out. So we are left with v by 2 ln of d by r d divided by x into d minus x. So I can write this v by 2 as v dash. It will be equal to ex v dash d into ln of d by r, this x into d minus x. Where this v by 2, you can see it from here. V is the voltage between A and B, and at point N, since we have to calculate the phase voltage, that will be VAN or VBN, that will be definitely VAB by 2, that's V by 2. So this V dash by 2 will be the phase voltage, V dash, between conductor A, let us say, and neutral point, where V dash is the voltage of the line to neutral. That is, now Ex is equal to K divided by X into D minus X, where K is equal to V dash D divided by ln of D by R, just to have an idea that this depends on X and D minus X. As X decreases, Ex increases. That means it is inversely proportional to X, and Ex will be maximum at X is equal to R. This also we know that the potential gradient will be maximum at the conductor surface. We have done this in case of cables. So Gmax will be equal to, or Emax or Gmax, I have told you in the last lecture of cables that they are one and the same thing. Sometimes we represent it by G, sometimes we represent it by E. So it will be equal to V dash d divided by r, sorry x, sorry r into d minus r ln of d by r. Since d is very large as compared to r, we can take d minus r approximately equal to d. So g max will be equal to v dash divided by r ln of d by r, or v dash is equal to g max r ln of d by r. So critical disruptive voltage, this is actually the value of the critical disruptive voltage, and it will be definitely in its SI unit will be in volts. We'll see later what will be actually its unit. I'll write it as volts. Critical disruptive voltage is the voltage at which complete disruption of the dielectric occurs. As I have told you that it becomes conducting at that time. This voltage corresponding to the gradient of the surface equal to the breakdown strength of the air denoted by G naught. So it also corresponding to the value of G naught at which breakdown of the air takes place, that is denoted by G naught. G naught at G naught is equal to 30 kilovolt per centimeter at NTP, that is at 25 degrees centigrade and 76 centimeter of Hg, that is pressure, 1 atmosphere. This G naught is actually dependent upon the atmospheric condition, that is on temperature and pressure, and that is taken care by this delta. It is known as air density correction factor. This delta is known as air density correction factor. It's quite simple. You'll see that the air molecules, the conductivity of the air depends upon the air molecules, how they are related to each other. As temperature increases, they expand, and as pressure increases, they come close to each other. That's why the conductivity will depend on both temperature as well as on barometric pressure, that is B. So in this case, this delta is given, it's an empirical formula given by the peak. It is given by 3.92 into B divided by T plus 273, where B is the barometric pressure in centimeter Hg. You have to take this in your mind. It is not in SI unit, it has to be in centimeter of the mercury, and T is in centigrade, degree centigrade. So here we can calculate this delta, and G naught at any value of temperature and pressure is given by G dash naught is given by G naught into delta, where delta is the air density correction factor at any value of pressure and temperature. So this is modified, this equation is modified now, V into R G naught, where G naught is actually G naught dash, sorry, this G naught dash is equal to G max, that is equal to G naught into delta ln of d by R into d by R, and now its unit is kilovolt, because you will see that G naught is given in kilovolts. You can see it from here, it is kilovolt per centimeter, that is total unit of this voltage will be now kilovolt. Usually here when we derive this equation, we assume that the conductor surface to be smooth, but sometimes it may not be the case. We may have some irregular surface of the conductor, and irregular surface play a vital role in case of this potential gradient, because potential gradient of irregular surface will be more as compared to the regular surface. When potential gradient is more, you will see that the disruptive voltage for that kind of conductor will be less. That means corona takes place at lesser voltage for an irregular surface as compared to the smooth surface. So in that case, we need to consider the irregularity surface factor. So irregularity factor is denoted by m naught. We have to simply multiply it by m naught, and this denotes the irregularity factor, and it is usually equal to 1 for polished surface, and for roughened or earthed wire, weathered wire, it is equal to 0.98 to 0.93. Definitely it will be reduced. 7 strand wire, it will be equal to 0.83 to 0.87. Long cables with more than 7 strands, it is equal to 0.9. So the cables or the conductors we have, the chances of this m naught will mostly be equal to less than 1, because polished wires are very less used in the in our this power system. Now this disruptive voltage is the voltage at which this corona starts, but it is not visible. This corona is also visible as well, and if the voltage increases beyond this critical disruptive voltage, the corona becomes visible. The voltage at which the corona becomes visible is known as critical visual disruptive voltage, and that is equal to, that voltage is equal to Vd into 1 plus 0.3 divided by square root of R into delta, where R is the radius of the conductor, delta is the air density correction factor. This also is an empirical formula. This is given by peak. This is given by peak, and it is denoted by, you just have to replace, or we can see VVD is this times VD. So we have to multiply the disruptive voltage by this factor, and we will get the critical disruptive voltage. One more thing, in both the formulas you will see that this G0 is equal to 30 kilovolt per centimeter for air, and its value is peak to peak. Its value is peak to peak. To get the value of RMS value, we have to divide it by root 2. So we will get this G0 will be equal to 21.1 kilovolt per centimeter, and its value will be now RMS value. So the disruptive voltage will be equal to 21.1 R delta M0 ln of D by R, and its value will be now in kilovolt, because G0 is in kilovolt per centimeter. Since you will see here, this is unitless delta, M0 is unitless, this ln of D by R is unitless. So the multiplication of these two should give us the value of kilovolt. Since this is in kilovolt per centimeter, that means R should be in centimeters. R should be in centimeter, and in this case, ln of D by R, there the unit of D and R should be same. It can be anything, but here the R should be in centimeters, because this G0 21.1 is kilovolt per centimeter. So to get it into kilovolt, we have to multiply it by centimeters. One more thing, here the critical visual disruptive voltage is given by R G0. G0 is again equal to 21.1 RMS value. Here it is MV delta 1 plus 0.3 into, this is the factor which it is used to convert into visual disruptive voltage, ln of D by R. In this case, again MV is equal to 1 for polished wire. It is equal to 0.72 for local corona on stranded conductors. Local corona is between the two conductors which is close to each other, and 0.93 to 0.94 is the rough conductor exposed to atmosphere severity. So this is also, but this MV is definitely different from the M0, and so you need to take care of these things. One more thing that you have to take here, that I have told you that this R should be in centimeters. Here also the R should be in centimeters. This is the peak formula, which is an empirical formula. So, and it is in the square root. This 3 comes up because to make it a unitless quantity, because this is actually a factor which is more than 1, just to make this disruptive voltage equal to the visual voltage. I hope you got this. Thank you.